Okay, doke. The title of this section should be first derivative and second derivative test, but it's actually how derivatives affect the shape of the graph. We're going to disguise some calculus with what's called curve sketching. Curve sketching is similar to what you did last year in pre-calc. You remember pre-calc last year where you had all those funky rational functions with asymptotes flying all over the place, and did it make a, did it go up and then down, and those parabola-looking parts and all that other stuff. We're going to eventually get to that, but before we get to that, we need to talk more about the calculus that will get us to those fancy graphs. Okay, so we're going to talk about increasing and decreasing. The other nice thing about this, by the way, is that you did most of this work in the last lesson. You were able to answer the questions when we were talking about Rolle's theorem and MVT to get us to things like what does increasing and decreasing mean. We've talked about extrema already, relative extrema versus absolute extrema. And we're going to check that with what's something called the first derivative test. So we talked very loosely about why is this thing, how do we know that this point is a maximum? And so we talked about things like, well, it's the top of the hill, or it's a minimum because it's the bottom of the valley, or we looked at the slope of the tangent lines. The nice thing about the first derivative test is it's very straightforward, very algorithmic, very easy to use. By the way, you do know what the word algorithmic means, yes? Okay, it's a step-by-step instruction. We're going to talk about something called concavity, which is, in simplistic terms, it's the shape of the graph. And then we're going to talk about point of inflection, which is a new term for you. We'll get to it when we get there. And then we're going to talk about the second derivative test. Now, the second derivative test is a little weird. Honestly, it's completely useless. So you're saying to yourself, Self, why is he teaching it to us? Because if I didn't teach it to you, there would be 3 questions about it on the AP test. Now that we spend the time talking about this useless tool, hopefully it won't show up on the test. But it's not difficult. It's just a waste of time, and you'll understand what I mean when we get to that. And then, I think we've used this one already, but again, on Monday, compliment 2 strangers. But again, try to keep it not creepy. All right, so we're back to the hill. We talked about Rolle's theorem, and you'll remember Rolle's theorem, the difference between Rolle's theorem and MVT is Rolle's theorem, you have to start on level ground and end on level ground, so you have to check the starting and ending point of the interval, whereas mean value theorem can be anything. But we talked about the fact that the top of that hill is a maximum. Yes? Yeah. And how do we know? Refresh my memory on how we know that that hill has a maximum at this point that we'll call B, as in Badger. How do we know that that's a maximum? Go.
Because there's no other point above it.
Good. Okay. Very simple. There's no other points higher than that. So that would explain why it's not only a relative max, but it's also an absolute max. There's no other points in that picture that are higher than B. Okay, good. Now, how do we know that it's a max mathematically?
The rate of change is 0 at point B.
The rate of change is 0. In other words?
The slope is flat, and the derivative is
Derivative is
0.
0. Good. In other words, we have a horizontal tangent line with a slope equal to 0, or dy dx is equal to 0. All of those things mean the same thing. So we talked about the idea that if I take this derivative and I find the critical numbers, I forgot, what are critical numbers?
Points where the derivative is either 0 or
Say again?
The derivative equals 0.
There are points that make the derivative equal to 0, or, bonus question,
or undefined.
even though I'm pointing to her, waiting for an answer, you're going to answer anyways?
Sorry.
Also where it's undefined. Good job. Okay. That undefined part is one of the elements that we have a tendency to forget about. It'll show up in some weird examples where you have denominators that make the rational function undefined. We also have to consider those critical numbers. We find the critical numbers. If the derivative of the tangent line is 0, it's going to be either a max or a min. and then we have to figure out which one. How do we figure out which one? Let's suppose we didn't have the picture. I just have a function. I take the derivative of the function, I set it equal to 0, I solve, and I find out that this point B is where there's a critical number. So I know that B is either at top of a hill or the bottom of the valley. How do I figure out which one it is? Without graphing it, without drawing a picture, without using Desmos. Just mathematically, how do I determine if that's a peak or a valley? Say again? Ooh, good. So like when we did the absolute maxes and mins, you could test y values. Okay, good. Jessica, what were you going to say? The derivative from the right and the left. Talk more about that. Okay, so let's assume, like this picture, B is a max. Well, that blue on blue does not work. We'll try green. Let's suppose B is a max. What would be true about the derivative over on this side of the picture? It'll be positive. And then, what would be true of the derivative on the right? Okay, so dy dx is greater than 0, and dy dx is less than 0. Good, we can use that. And then if it was a valley, yeah, we'd flip it over to be the opposite. Okay, is this making sense to everybody? It seems like I'm beating a dead horse, but I think if you understand the basics of what this means, and it'll make it easier when we start doing things like how to work with it. Okay? Let's get rid of this mess, and let's go here. Okay? We did this already, but we're just going to put it in fancy mathematical calculus speak. If the derivative is greater than 0, then the function is increasing. If the derivative is less than 0, then the function is decreasing. Well, what does that mean? If the slope of the tangent line is positive, it's going to be going uphill. If the slope of the tangent line is negative, it's going to be going downhill, so known as decreasing. But again, we did this already, so we're good to go here. Yes, we just give it fancy terms, increasing and decreasing. All right, so now that we're done talking about the understanding of the theory, let's do the actual practice. I would like to know where on this function it's increasing and where on this function it's decreasing. But in order to do that, you're also going to have to figure out where it's doing neither, also known as critical numbers. Okay, so here's what I'd like you to do. Take the derivative, find the critical numbers, and figure out where this function is, the derivative is positive, and where the function has a derivative that's negative. Go ahead. Critical numbers. But do we care about what happens at 0 and 1? Let me ask you a question. What's happening at 0 and 1? Correct. It's either a hill or a valley, right? Did I ask anything about hill or valley? I just want to know where the function's going up and goes down. Now, if you want to do that, you could Well, the good thing is everybody's doing the same thing for the most part. The bad thing is it ain't really what you need to do. Okay? What most of you are doing is telling me about the points 0 and 1. Right? So what's happening at 0 and 1? Allie?
It's a turning point.
It's a turning point, also known as a peak or a valley. Notice the problem doesn't ask you anything about that. So hold on, let me write some notes down here. So, do we all agree that the critical numbers are when x equals 0 and 1? Yes? Okay. So one of those is probably a max, one of those is probably a min, but I didn't ask you that. I asked you about the other points on the graph. So how many intervals do we have to worry about? 3. Good. So we care about the interval going from negative infinity up to 0, from 0 to 1, and 1 to infinity. You with me so far?
Yeah.
And I kind of set you up for failure here because I didn't show you how we can organize this information. So I'll do that now. We got this information. I know that 0 and 1 aren't critical numbers. They're a peak or a valley. They're a max or a min. They're both. They're neither. Whatever. Okay. How do we organize this material? So we're going to use. Whoops. I had the wrong slideshow running. Okay. Talk amongst yourselves for 30 seconds.
Because the original function is
And we're back to our regularly scheduled program.
Yeah.
Okay, so we did that already. Found critical numbers. Now, how do we organize the information to make it very clear on the stuff that we need to get from this problem? We're going to use something called a first derivative number line. Okay. And what that's going to do is give you a nice, easy way to organize all kinds of data. You're going to do a ton of these things. And the reason you're going to do a ton of these things is that they give you so much information in one little picture that you just can't beat it with a stick. Okay, so you start with a number line. And you label it. Labeling it seems overly picky, but it's crucially important. Because you'll see later, we're going to have a different type of number line. Is that better? Okay. On that number line, you're going to put your critical numbers. So now we get what Liam was talking about. We've taken that number line and we split it into 3 regions. And here's where things get a little kooky. Let's talk about the interval from negative infinity to 0. How do I know if that region is increasing or decreasing?
You plug in a number
Beautiful. Hold on, plug a number into where?
to the derivative.
Good. Now, it seems like I'm getting very nitpicky. This is very important. The reason that's there is it tells you where to plug numbers in. This is where we have fun. Babe, give me a number to the left of 0 that you would like to use.
Negative 1.
-1. Give me another example. Get a little crazy on this one.
Negative 300.
-300. Could you get crazier still? I asked the wrong question. Babe, get crazier still and tell us another number.
Negative 547.
Love it. Okay. It doesn't matter what you want to choose, as long as that number to the left, that number is to the left of 0. So if you take a number like, we'll go back to the original number, -1, and you plug it into the derivative, will you get a positive or a negative answer? Is that you? That's you? Can I get a confirmation? Anybody else? Positive? Beautiful. Okay. Now, I only care about the sign. Some of you are going to plug it in and tell me the value. It doesn't matter. The value is irrelevant. What's important is just the sign, S-I-G-N. So if you plug -1 in, if you plug -300 in, if you plug in -500 in, 47, whatever she said, the signs are all going to be the same. What's a good number to pick between 0 and 1? 1/2 works great. And how about to the right of 1? 2. When you do that, you end up with this. I'll talk about the arrows in a second. Underneath the number line, I'm labeling it as all of the numbers to the left of 0 will give me a positive value. You did say positive, right? All the numbers between 0 and 1 are going to be negative, and all the numbers to the right of 1 are going to be positive. First crucial mistake. People find one region and they assume that it always flips back and forth. So you find the first one is plus, so it must go plus, minus, plus. First region is negative, it must be negative, plus, negative, plus. No, you have to test every region. I don't care what number you're plugging in there. Notice I have no indication of what number I used. I'm trusting you to be able to figure out whether it's positive or negative. The arrows indicate the direction of the graph. So obviously, from negative infinity to 0, the function is increasing because the arrow is going up. From 0 to 1, it's decreasing. Now you might be saying to yourself, Self, why can't we just write increasing and decreasing in there? You can, but what I have found is that by drawing the arrows, it helps you get a feel for what the function looks like. Okay, so notice we started with a cubic, did we not? If you look at those arrows, you see that the graph kind of has a shape like a cubic. Okay. Now, based on what Jessica told us earlier, if you look at 0, is 0 a max or a min? It's a max. Does everybody see why? Not only if you look at the picture of the arrows, you can tell that it's a hill, but also based on what we talked about earlier, the derivative is positive to the left, negative to the right. And then, Captain Obvious here, what's happening at 1? It's a valley, yes. Okay. Or a relative min. All right, questions on this procedure. This is the best way to stay organized when you're dealing with the first derivative test, which we'll get to in a second. Are we good? Okay, excellent. We talked about that already. Beautiful. Let's move on. So now we get the official first derivative test. The first derivative test is not going to deal with increasing and decreasing. It's going to allow us to answer the question at those critical numbers. Hold on. They're going to allow us to answer the question that all of you were trying to do, and that is there a max or a min at the critical numbers? And all you have to do is draw that picture. Okay? So here's a picture of the function that we had before. It is a cubic. That's what it looks like if you graph it. And our answers were correct. There's a relative max at 0. There's a relative min at 1. Okay. All right, so here's the fancy schmancy first derivative test. You take your critical numbers, and you've got 3 possibilities. Does it go positive, negative, which would make it a max? Does it go negative, positive, which makes it a min? Or the third case is maybe it doesn't change sign, and we don't have a max or a min. That can also happen. And I got some examples to show you what that looks like. Think about the difference between the hill and the valley. It's going to be a hill if you go up and then you come back down. It's going to be a valley if you go down and then come back up. Is this making sense? From a theoretical standpoint, not necessarily an application standpoint. I've got a couple more application examples for you, but I just want you to make sure you understand what we're doing. And then we'll have some more practice on how to do it. Okay, so here we go. Now notice I changed the problem. Now I'm focusing directly on extrema. So before you even dive into it, let's talk about this cubic. It's a cubic. And what do you know about a cubic? What are we probably going to get for answers? Say again? 1 max and 1 min, theoretically. Now maybe I picked a weird example, but theoretically we're getting a max and a min. Your job is to find out where they are and why they are. a max or a min. Go ahead. Don't be bashful about busting out those calculators. If you don't want to factor a quadratic, use your quadratic formula. I don't care. Try to get all your bits and pieces of your first derivative number line correct. Don't forget labeling that number line. Don't forget your plus and minus. Don't forget your arrows. I spent a lot of time with people down in Southern Illinois this weekend, so I'm remember the accent. State line. What's that? I see. But they bring us. Grew up from a school called up in Illinois. A girl went out, and then it turns out later she's the superintendent of the elementary district.
What did you throw her out for?
Mouth. She was just angry.
Did she cuss you out?
Oh, she did.
Why? Like, you just like, well.
No, I just asked somebody at the table, "Do you get security?" And they walked her right out. It was awesome. Yeah. Is that your y equals?
Yeah. But it doesn't, it's just, if someone click on their y minus, I mean y
Yeah, we're not doing that. Remember, we're not doing absolute max and min, so there's no t-chart here. It's a first derivative number line. The reason I'm saying you would think on putting an F prime there is because that'll tell you what it plugs into. So you're going to tell me and I would plug it into, all you need to look at, since you have to just look and see if you put a number in, does it make that positive negative? Does it make that positive negative? You know the positive negative. I don't care about the number, I just care about the sign. After I give you a couple more minutes to work on this, I'll show you some other techniques to help test regions. Like, for instance, you could put the function into y equals and look at your table. Get to a region you need and look at the numbers in that region and see if they're positive or negative. You could use something called Bernoulli's principle, I think it is. Or you could just plug and chug into the home screen. I'm so glad you caught that now instead of later.
Yeah.
Present. Kurtz. Alright, I blame Kurtz because it's not me. It's Kurtz's fault. If he was here, we wouldn't have had that problem.
Yeah.
Okay, we good? Beautiful. Let's see what I got when I click. So whoops. I guess I didn't write it down. Whoops. Come on, Reedy. F prime of x is equal to 3x squared plus 2x minus 5. So factor quadratic formula. Critical numbers happen when x is equal to, little help please.
1.119.
Negative, you know how Grandpa Selmer would say that? Negative 5 turds, correct. And? 1. Okay, good. I'll trust you on that one. But obviously you see I used my my quadratic formula. Again, this is important Not only because we'll get different number lines later, but it also tells you where to plug numbers into. They have to go on the number line in numerical order. Okay, now that seems like a silly statement that I think you all realize that negative 5/3 or negative 5/3 is to the left of 1. However, when you get into things like the square root of 3 over 2 versus the square root of 5 over 4, which one is bigger? You need to figure that out, otherwise you're going to get all kinds of wonky ideas, or answers, I should say. Okay, so how am I going to test some numbers? Well, I could just plug into it, and in fact, I was talking to Amanda about this. How does this thing factor? 3x minus plus 5 and x minus 1, yes? Okay, when I'm plugging numbers in, I go right to this bad boy, because I just care about whether or not it's positive and negative. And we all know that a positive times a positive is positive. A negative times a negative is positive. A positive times a negative is negative. So I pick a number over here. What's a good number to pick over there? I don't know, negative 10. Okay? I'm not even going to mess around with getting too close to it. I'm going to try negative 10. If I plug negative 10 in here, this is negative. This is negative. A negative times a negative is positive. I got that right, didn't I? Okay, good. What's a good number in here? Hot diggity. Positive times a negative is negative. Decreasing. 10 gabillion. If I put 10 gabillion in there, I get a positive and a positive, which is positive. And there's my first derivative number line. So what do I know? From that little picture, I know where the function is increasing. Do we need a review of interval notation, or are we good to go?
Can you do it real quick?
Sure. It's increasing from negative infinity to negative 5/3 union negative 5/3. No, I lied. 1 to infinity. Okay. Bracket or parentheses at negative 5/3. Why?
Because it's not like the derivative 0 at 5 or negative 5/3, so it's not increasing or decreasing this.
If you put 50 calculus teachers in a room and ask them that simple question, they would argue for hours. So what we're going to do is we're going to go with parentheses. I would argue that it's neither, because exactly what you said, it's neither increasing or decreasing, so we don't include it. Decreasing from negative 5/3 to 1, parentheses. And you know never to put brackets around infinity and negative infinity, right? We're good to go there? Okay. All right, so not only can we tell now where the function is increasing and decreasing, we can also tell about negative 5/3. What happens at negative 5/3? Say again, Ms. Gary? Good. What else can you tell me about what happens at that point? Good, it's a relative max. And at 1, we have a relative min. We good? Okay, beautiful. Let me get rid of this mess because this is important. The College Board, i.e. the AP, can be sticklers about this. They want you to be able to denote that you understand what's happening at that point because of your calculus knowledge, not because you use your graphing calculator, you cheat off the person next to you. So they like when you write about math. Okay, this is going to get old real fast, but if you want to explain why there's a relative min at 1, you write a sentence that looks like that. A relative min occurs at x equals 1 because f prime changes from negative to positive. Which again relates right back to your number line. There is another version of this that I'm not going to talk about yet. We'll get to it later. I just want you to make sure you understand this because again, like I said, this relates back to the number line that you've already created. Relative max occurs at x equals negative 5/3 because f prime changes from positive to negative. Now you knew this before I even clicked on the slides because we've talked about it already. But again, they like you to write about math. So we'll practice that over and over again. We good? Okay. Anybody need a couple more seconds, or are we good? We're good. Okay. One more for you. By the way, I've already factored it for you. Please don't distribute that x to the 1/3. That would be silly. Zero product rule. What? My shoulders are getting sore from carrying that guy. These days.
You also asked about if the rumors were true that you blame everything on him.
And what did you tell him?
Yes.
Good, so you told him the truth.
Yes.
And how did he react?
He apologized.
Yeah, we got a lot of apologies.
Good, good, good. And he should. I mean, how many times are we gonna give him a break? We actually started tracking Knupke's mistakes too from my geo classes.
But did you have time? Doesn't she have
No, it's 9.5. See how the slash doesn't go all the way through?
What was that?
It was a questionable homework assignment that she kind of screwed up on, so I didn't feel good giving him a full point on that. So when it gets to 10, I have to convince her to buy my class these donuts. For those of you that know Knupke, you know how well that's gonna go over.
It's not gonna happen.
It's not gonna happen, no.
It's possible.
I get it.
No, but it's
It
possible.
is, it's possible in the same way that me quantum tunneling over there is possible, you know? But it's not like,
Maggie! You wanna come and play with the big board? You don't have to, I can dictate for you, or you can come and play with the big board, it's up to you. Oh, great, so you're gonna make me work, okay, fine. What's the derivative?
Negative x to the 1/3 plus 1/3 parentheses 8 minus x. And then
Wait, 1/3 what?
1/3 parentheses 8 minus x. And parentheses. And then x to the negative 2/3.
How'd she do? Good? No problems? Excellent. So, remember we talked about getting into that nastiness that is being able to factor, and this is where it comes up in this problem also, in that we don't want a sum, we want a product. I'm going to factor out what they have in common. Set it equal to 0. So I'm going to take an x. Do I take an x to the 1/3 or an x to the negative 2/3 out? Good, negative 2/3 out. Okay. Why? Because that leaves a negative 1 behind. I lied. A negative x behind. X to the 1/3 divided by x to the negative 2/3 is x to the first. Plus, that's gone. 8 thirds minus 1/3 x. Are you with me? Am I okay so far? Okay. That means that x to the negative 2/3 times negative 4/3 x plus 8/3. Gabriella, what are my critical numbers then?
0 and
2. Before we go any further, I want to talk about that 0 value. Everybody agrees that it's 0, yes? But notice, that's not where the function equals 0. That's where the function is undefined, because this is a negative exponent. Right? It's irrelevant in the way we proceed with the problem. but I just wanted you to make sure and reiterate the fact that when we look for critical numbers, we're looking for where the derivative is equal to 0 and where it's undefined. Okay, so we're good to go. Excellent. What's next? Make a number line. I need some working room here. Over here. F prime of x. I got a 0. I got a 2. To save time, how does it go moving from left to right? What's the first region, positive or negative? What the first, this region over here, to the left of 0, this region there is over here, this area. Is it positive or negative? Over here, this bit, right here, on the graph over here, this graph. What this region here is positive. Are you sure? Hello, is this still on? Testing. So let's be sneaky about this, or actually not sneaky. Let's think about this from an intelligent person's approach. What can you tell me about this number or this expression? Anything interesting about that? Good. And what if I plug in a negative? Oh, you said that. What if I plug in a positive? Positive. It has a square in it. Because remember, x to the 2/3 is the cubic root, and you square it. This bad boy is always going to be positive. If you notice that, it'll make your life a little bit easier. If you don't, that's okay. You just plug and chug. What's a good number to plug in here between 0 and 2? 1. Is it positive or negative? Well, let's see. Positive. If I put 1 in here, I get negative 4/3 plus 8/3 is positive. Oh. What if I plug in a big honking number? Still positive here. Big honking number over here makes this negative. Whoops. Increasing, increasing, decreasing. That's why you have to test every region. All right, so let's do the easy one first. What's happening at 2? Give me the sentence.
Behind the side. Because you're moving the chair.
Perfect. You all heard that right? Good. Most of you were singing along. What happens at 0? I have no idea. I don't know what the graph looks like. Okay. But it's not a max or a min. Okay? Any questions? We also have increasing and decreasing, but we don't care about that. All right, now bust out your calculator or Desmos and graph the original function and tell me now, looking at the graph, what's happening at 0. What does it look like? Why did we get a critical number and not a max or a min? By the way, given both tools of the calculator and Desmos, I would automatically go to Desmos. If you haven't used Desmos, I would say you should get in the habit of using it. It's a great graphing tool. But if you want to use your calculator, you can, because it's American. What's that?
When you factor, how do you factoring out the x to the negative 2/3 of negative x?
Because factoring is dividing, right? Okay, so what I'm doing is I'm dividing x to the negative, x to the 1/3. I'm dividing by x to the negative 2/3. So that when you divide exponents, you subtract the exponents. So 1/3 minus negative 2/3 becomes x to the 3/3. It's the same thing. That's why we take the more negative one out. What's it look like?
Yeah, that makes sense.
It like a hole.
It looks like a parabola falling over, yes? Okay. For those of you that didn't graph it, it looks something like this. Okay. A what? Parabola in the wind, good.
Wait,
In a westerly wind.
like it like skips. Is that normal?
That's just because your calculator can't handle that region close to zero. So it just chooses, I don't know how to do this, so I'm just not going to graph it. That's not
Okay, that's why
intentional.
you should use decimals.
Yeah, maybe. Because once you have it at decimals, you can pinch it, stretch it, you know, you can move it all over the place. Okay, we good? We honestly don't care what the graph looks like. I just wanted you to see a situation where you get a critical number that's neither a max nor a min. Good. Any questions? Can I erase this? Okay.
So are the critical numbers that are equal to like undefined, is that never going to be maximum or what?
I hate to use words like never or always,
Yeah.
but most of the time, a critical number that comes from an undefined value is usually going to create a funky point.
Okay.
Okay. All right, concavity. Let's talk about the theory first. Concavity is the shape. Okay, so think of concavity like a bowl or an umbrella. Umbrella. Okay. Will it hold water or does water run off of it? It depends on the shape of the curve. So if you think about a parabola that's opening up, positive coefficient, it's like a bowl. It would hold water if you pour it into it. If you flip that parabola over, you have an umbrella, which water would just run out of it. It's not going to hold any water. That's all concavity is. This comes about from, okay, so let me read one of these just to show you how ridiculous it is. F is concave up if at A, if the graph of F is above the tangent line to F, at A for all x in the neighborhood containing A, but not equal to A. So everything's cleared up, right?
Yeah.
All right. Let's look at a picture first. This might help. Let's start with something that's concave up. So concave up is the same thing as a basic parabola. If I draw any tangent line to that graph, the tangent line would be below the curve. Right? I come over here, and I do a tangent line over here. That tangent line is below the curve. If I flip it over to something called concave down, then any tangent line to that curve would be above the graph, which is what they're trying to say in that little rectangle looking thing. Okay, so we're going to keep this really simple. Let's talk about the bowl here. What can you tell me about that point right there? It's a relative minimum. Why?
Because the derivative to the left is negative and the derivative to the right is 1.
Perfect. She just reiterated everything we've done for the last 40 minutes. But I'm going to suggest a different reason. That shape is opening up. The point is at the bottom of the bowl. It's got to be a minimum. Does that make sense? So you'll see me do this a lot. Okay, we've got, it's concave up, and we have a critical number. It's got to be a min. Does that concept make sense? Okay. The same argument could be made for that point. We have an umbrella. We're talking about a critical number for the umbrella. The top of the umbrella would then become a max. And again, I'll ask once more time. One more time. Does that make sense? If it does, then the second derivative test will be pretty simple. If it doesn't, we may need to go a little bit more in depth in it. Because we're going to start looking at concavity. Okay, moving on. Here are all the different types. This is basically what I just did with my own little bowls and umbrellas. Okay, we got a bowl over here above the tangent lines. We've got an umbrella below the tangent lines. And then we've got the third one, which is all the funkiness. Notice that in the left picture, that graph is always concave up. It's always part of the bowl. The one in the middle is always concave down. It's always part of the umbrella. In the left picture, it switches from concave down to concave up. That point where it changes, they have it labeled as A here, is what we'll talk about in a second, but it's called a point of inflection. It's where concavity changes. And all of this relates to the second derivative. So here's the concavity test. If you understood increasing and decreasing, just replace increasing and decreasing with concave up and concave down, replace the first derivative with the second derivative, and we're golden. If the second derivative is positive, it's concave up. If the second derivative is negative, it's concave down. Whoops, jumped the gun there a little bit. Okay?
The second derivative, you mean like, oh, okay.
Yeah, now we're going to start taking the derivative of the derivative, second derivative. Okay, so we're going back to the same cubic we had before. What I would like you to do is take the derivative, skip all of the increasing, decreasing, max and min garbage, take the second derivative, and figure out where that graph is concave up and concave down. In other words, where is the second derivative positive and negative? And yes, you will have to find critical numbers for the second derivative. Carry on. How we doing? Good? Okay. Yes? Critical numbers at negative 1/3? Hot diggity. Second derivative number line. So we haven't seen this yet, but I'm sure you could figure it out. You draw a number line and you label it as the second derivative. And the process that you went through before, rinse and repeat. Slap negative 1/3 on there, test a region, which with one small change. You're not going to put arrows above it. You're going to put CD for concave down, CU for concave up. So we get two things out of there. We find out where the regions are We find out about the concavity of the regions, but we also find out something special about the point -1/3. -1/3 becomes what I called earlier a point of inflection. And I got a couple more slides on that in a second, but I want to introduce it now. It is a point where the concavity changes. On the first derivative, if the concavity changes, we get a max or a min. On the second derivative, if the concavity changes, we have a point of inflection. Okay? Questions? Beautiful. Now let's try something a little bit more interesting.
So this is the concave upward, is that what we said the last one?
Say what?
Is like, how do we, like, we said this concave upward, then?
You don't need a sentence for that.
Okay.
Is that what you're asking?
Okay, you just, oh, okay.
Okay? Good. Before you dive into this too deep, let me ask you a couple questions. Does this function ever equal 0? This function, not the derivative, I'm just talking about what we're looking at, this rational function. No. Why not, Allie?
Because there's no x on top.
Good. Yeah. A function will be equal to 0 if the if the numerator equals 0. That can't equal 0, so we move on. Where is this function undefined? Are you raising your hand?
Yeah.
Go ahead.
Plus or minus 1, 3.
Perfect. Okay. Now repeat that process by finding the first derivative. You can find the critical numbers, but you don't have to. Nobody cares because we're going right to concavity. Then find the second derivative and test some critical numbers. Okay. Now I want to get through this quickly, so we're gonna skip all the work on here, but you understand the process. The only thing that's different here is that you're going to get some critical numbers that might come from the denominator being equal to 0.
What did you say about root 3?
It's where the function is undefined.
With that one?
Correct.
But if it's root 3, isn't it just 6? 6 over 6?
Oh, that's a plus sign.
Yeah.
Yeah.
Allie, you led me down the dark path.
No.
Let's start over. Where is this function undefined?
Nowhere?
Nowhere. Good. That's what I thought you meant. And you said it so convincingly, I'm like, hell yeah, girl, let's go. And then I realized you had no idea what you're talking about. That's okay. We still love you. Let's move on. Yeah, so big blank screen, but again, taking that function, take the derivative of it. I would not do it as a quotient rule. You can if you want, but you don't have to. And then solve for some critical numbers. Okay, the process is the same. If we had more time, we'd work through that, but I want to get to this point of inflection, give you the fancy schmancy definition. It's a point where the concavity of the function changes. They will sometimes be hard to recognize. If you look at my picture up there, notice that from A to B, it's concave down. And then this rando point out in the middle of nowhere called B flips over the graph. So we go from umbrellas to bowls, bowls to umbrellas, umbrellas to bowls. Ooh, umbrellas to umbrellas. So you're wondering, well, how can I go from concave up to concave up, and why do we have a break here? Because something weird is happening at E. If you were to look at the function for E, you would see E as being a critical number, but you wouldn't see a change in concavity. Most commonly, the thing that bothers people is these points of inflections are sometimes hard to find because they're in that point of weirdness. It's not something as distinct as the peak or the valley of function. We'll also skip this because I want to get to the second derivative test because that's going to cause the most problems. But let's talk about how you would solve this problem. All I've done in this is thrown another step into the concavity thing. Take the derivative. Take the second derivative. Find the critical numbers of the second derivative. Slap them on a second derivative number line. And anywhere that CD becomes CU or CU becomes CD, those become points of inflection. Okay? Questions? I got that, we can do that. Okay, so now we find our critical numbers for the second derivative would be 0 and 2. And then, yeah, I think I added all of them, maybe, okay, okay, boom, there we go. This one is more traditional, it goes concave up, concave down, concave up. I'm sorry?
Do we ever have to draw the graph?
Eventually, yes, we're gonna do some curve sketching, but not a ton of time on it. It's not much different than what you did last year, except we use calculus to find a couple other things and just make the graphs look prettier.
Okay.
But we don't spend a ton of time. Okay, up until this point, I haven't talked anything about the second derivative test. The second derivative test has absolutely nothing to do with points of inflection or concavity. That is a big mistake that people make. The second derivative test, strangely enough, is actually going to help you determine maxes and mins. So now some of you have already gotten it. Why would I bother doing that when I already have the first derivative test? It is an excellent question for which I have no answer. Other than some melonhead at the College Board is going to say, we should test them on the second derivative test, the thing that nobody ever uses. And again, if I didn't show it to you, I would feel bad about it. So let's talk about the second derivative test. Okay. So think of my thought process here. I give you a function and I ask you to find the relative extrema. You take the derivative, you find the critical numbers, you put them on a number line, a first derivative number line, you test regions, and boom, all the information you need is sitting right in front of you. However, the second derivative test then says, no, we're not going to do that. We're going to take the first derivative, we're going to find the critical numbers, then we're going to take the second derivative and find the critical numbers and then put that together. So it is a little confusing, but it relates back to the idea of the bowl and the umbrella. If I know I have a critical number, and I know I have a bowl, that's got to be a minimum. If I have a critical number from the first derivative and I know I have an umbrella, it's got to be a maximum. Okay, so here's the fancy calculus speak. Two things have to happen. F prime of c, whatever this mysterious number c is, has to be equal to 0. In other words, it's a critical number for the first derivative. And we need to know about the second derivative. If it's positive, it's a min, because now we're looking at a concave up. So we've got that bowl with a critical number. Part B is we've got an umbrella with a critical number. Going to be a max. So can you all appreciate how silly this is? Okay, good. So we're going to kind of go through it quickly, just so that you understand it and you know it. Then we'll practice it a little bit, and then you're probably going to forget about it until I ask you to do it. This is the type of problem you'll see, either from me, to make sure you learn the second derivative test, or from the College Board. They will ask you specifically to use the second derivative test. Nobody in their right mind volunteers for this approach. It's not that it's bad, it's just too much work. So as we get started, please find the first derivative, the second derivative, and the respective critical numbers for each of those derivatives. You work, I'll work, we'll get to the same point. Go. I'm going to be a rebel and not find the critical numbers of the second derivative test, or of the second derivative. I'm just going to stop there. Everybody good so far? I make any mistakes, or are we okay?
Um,
What did I do wrong?
2x squared and the
it's the second derivative.
Oh, thank you. Yeah, because 30 times 2 is 60. God, it's amazing that I'll be teach math. Okay. In order for the second derivative test to be applied, we just have to do one simple thing. I have to take the critical numbers from the first derivative and figure out what f double prime of those numbers are. So in other words, is f prime of 0 positive or negative? Sorry, is f double prime of 0 positive or negative? Is f double prime of 1 positive or negative? Is f double prime of negative 1 positive or negative? I don't care what the values are. All I care about is the, nope, is the signs. So if I plug 0 into the second derivative, is it positive or negative? Neither. Ooh, we'll come back to that. That's going to require some discussion. If I plug 1 into the second derivative, do I get a positive or a negative value? Negative is correct. And if I plug -1 into the second derivative, do I get a positive or a negative or a neither? It's positive. Have I lost anybody yet? Okay, now we summarize. We'll skip 0 for a second. Yes, Chris?
How would you find the critical numbers for the first two?
Because that's where my max and my min are going to happen. Remember, we're looking for a relative extrema, not points of inflection. Points of inflection come from the critical numbers of the second group.
So wait, do we need the critical numbers?
We don't. I was overzealous when I was explaining the problem. So I'm good with all this information. Okay, so let's talk about at 1. Is it an umbrella or a bowl? Umbrella or a bowl? A bowl. Because if the second derivative is negative, it's concave up or down? Concave down. Is that an umbrella or a bowl? It's an umbrella. Concave down. Whoop. Therefore, at 1, is it a max or a min? Max. Okay, good. This is ridiculous, isn't it? It's going to get worse. Hold on. At -1, my second derivative is positive. Is that concave up or concave down? Oh, you guys are good. Umbrella or bowl?
bowl.
Good. Max or min? Min.
And the boys at 9.
Okay. Beautiful. You got it. What about at 0? At 0, it doesn't work. You can't use the second derivative test. So you got to go back to the first derivative test. Again, I'm just going to come out and say I'm sorry. I can say I showed it to you. I'll give you a test problem or 2 on it, and then we'll move on. Okay. What I really want you to get out of this is the fact, or is how this second derivative works. This is what's important in my opinion. Whoops. This is what's important. Understanding that if you've got an umbrella and it's a critical number, it's got to be a max. If you've got a bowl and a critical number, it's got to be a min. So you've got a perfectly good testing method in the first derivative test. Let's stay with that. If you want to use a second derivative test, or some knucklehead teacher asks you to use a second derivative test, then you're going to have to do it. So just make sure you understand it and can work from there. The reason I don't like the second derivative test, aside from everything else we've talked about, is there's a really good chance that you might get a point where it doesn't work, and you're gonna have to go back to where you wanted to be anyways. Yeah,
Is there like why would you do it? Like is
for
there,
two simple reasons. I ask you to, or the college board asks you to on the AP test.
There's no like practical reason for it to be
Nope.
like it existed.
Nope. Nope.
Like, you know how like people say like, when are we gonna use this in real life? And it's like, well, you might, but this is actually an example where you probably won't, right? Second
I
derivative.
can't think of a single situation why you would have to use a single derivative
Came up
test.
with this.
It just happens to work.
I don't want these weird calculus nerds.
Maybe
He just wanted something named after himself, that's all. Mathematicians name everything after, Fermat's last theorem. You know, it's just a bunch of
Do they
egotistical.
name like if you make a theorem, do you name it after you or do other people? Or do you-
Having never created my own math theorem, I don't know the proper procedures.
It's like a rule that like the first person discovered it, they get dibs. So,
Yeah, it's called opening a textbook. All right, so blah, 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 blah. Okay? Beautiful.
Probably good thing we didn't have this slideshow.
All done. As you're doing the homework, knowing where we're going, the best thing that you can do to help yourself is to not think about what you're doing. Does that make sense? Okay, what I mean by that is, don't get caught up in the algorithms where you're just doing something because you think that's what you're supposed to do. Take a couple seconds and say to yourself, self, why am I doing this? Why am I finding the second derivative? If it has to do with max and mins, you're wasting your time. Okay. So understand what you're doing more so than how to do what you're doing. Some of these problems are going to get a little nasty, but we're going to crawl before we run. And that is, you'll see some simple polynomials where you're practicing concepts versus application. Okay? Beautiful. I would highly encourage you on Wednesday to bounce ideas off of each other and to work with people. Most of you do that already, but it helps a lot to work with other people to say, well, this is what I got. Did you get the same thing? And if you didn't, sometimes that's a good system because trying to figure out what you did wrong or what your group did wrong, you can learn a lot more from than just breathing through the homework. Okay? Questions?